Hello class. Today we're starting a new chapter, the acid-base chemistry and equilibria basically. I've already uploaded all the notes for chapter 16 and I used my back camera so you can see it. You probably can either watch it on your phone, take a screenshot of each page and then you'll be able to blow it up and copy it, or watch it on a TV and pause. I've focused about 3 seconds on each page so you can pause it easily and then proceed to the next page. So I'm not going to do too much note writing except when it helps the explanation, because you have all the notes already, all 16, 16 pages of notes. It's all on that, hey Teresa. So it's all on that video I uploaded preceding this one. You'll see it on my site, and then I'm going to create a playlist with all the chapters in it. I don't know why I didn't think of this earlier. I should have just done that a long time ago, and I would have saved a lot of paper. We'll see. So eventually I'll have a playlist. Hi, Raksha. I'll have a playlist. I'll put all the chapters in that playlist, so that way, even if you forget your answer keys, you can always go refer to the videos. So there's 3 different definitions of acids and bases. There's the Arrhenius definition, Bronsted-Lowry definition, and the Lewis definition. And each one is a bit more comprehensive. The most comprehensive one is the Lewis acid definition. Bronsted-Lowry is probably the one that has the most application in what we're doing. And then there's Arrhenius, which is the most simple one. The Arrhenius acid is something that creates H plus in solution, and Arrhenius base is something that releases OH minus in solution. Bronsted-Lowry acid involves, and base, Bronsted-Lowry acids and bases involve the transfer of H plus ions. So a Bronsted-Lowry acid is a substance that can donate a proton to another substance, whereas a Bronsted-Lowry base is a substance that can accept a proton. So ammonia is an example of a Bronsted-Lowry base. So how does ammonia is NH3. How does it create a higher concentration of hydroxide in aqueous solution? Well, if you take ammonia and put it in aqueous solution, for which it has a high solubility, what happens is, I should redraw it properly. There's a lone pair on the nitrogen, and the lone pair on the nitrogen can abstract the proton from water, and then the bonding pair that's between the hydrogen and the oxygen gets transferred to the oxygen. So what you get is the conjugate acid of ammonia, which is ammonium. So here's ammonia. Here's water. Then you get ammonium. And then the water, having lost the proton, becomes OH minus. So the presence of ammonia in aqueous solution creates an increase in the concentration of OH minus, but it's not because the ammonia is directly releasing OH minus, it's because it's abstracting a proton from the water. So an acid and a base always work together to transfer a proton. That's why you would call this the base. You would call this the acid. The water is acting like an acid here because it's giving up a proton. And then the result is a conjugate acid, because ammonium is a conjugate acid. Where's Mama? Where'd he go? There he is. And this is the conjugate base. And this is for, today's April 13th, right? Yeah. And it's day 10. there's an exercise on page 672 of the text where they ask you to show the conjugate acid base pairs for hydrogen sulfate. So we could do that. So yeah, it works. I already did it with water and ammonia. Now let's do it with HSO4. So sulfuric acid, when it dissociates the first time, you get hydrogen sulfate, or you can call it bisulfate. That's also an acid. Mind you, it's a weak acid. And if you combine it with ammonia, which is a Bronsted-Lowry base, it'll donate a proton to the ammonia, so you'll get the sulfate anion, and then the ammonia will become ammonium. So this would become the conjugate base. And this would be the conjugate acid. They have a couple exercises on page 673 where they ask you to pick out what's what, and I did it in the notes, so we'll skip over that and continue to the harder stuff. That's pretty straightforward. On page 674, they show you an example of how alkali metal oxides can make the water turn basic. So they ask you for the example of lithium oxide. If you take lithium oxide, and you'll see why they're called alkali metals and alkaline earth metals. Lithium oxide is Li2O, and if you show it dissociating in water, you could say Li plus aqueous plus oxide aqueous. Now that's not really going to persist for very long in aqueous solution. What really happens is the oxide anion combines with water and you get two hydroxide ions because it pulls a proton off the water. So the oxide anion does not like to sit in a water solution. It will react with the water and you'll get two hydroxides. So if you add lithium oxide to water, you'll get a basic solution. That idea has been known for quite a while. I mean, in the old days, people used to take the ashes from the fireplace, and wood contains a fair bit of sodium and potassium, and once you burn the wood, the potassium and the sodium that was in the wood gets turned into the oxide. Hi, Rebecca. So when you have oxides of sodium and potassium in water, the addition of the water causes them to react. You release the oxide ion, which then reacts with the water, and you get a basic solution. So in the old days, they would use the ashes from the fireplace. Hey, Temmie. And they would mix it with animal fat, and they would make soap with it, because when you mix animal fats with a strong base, you get what's called a saponification reaction, where it hydrolyzes. Hi, Nightbot, whoever that is. When you mix a strong base with animal fats, the base will hydrolyze. It'll break the fat into two, and you get glycerol and 3 fatty acids. And the fatty acids are what produce soap. You've all heard of palm olive, right? Palm olive is a soap that's made from olive oil and palm oil. So they put the two words together. And so you can take any fatty acid, either vegetable oil or even animal fats, and if you treat it with a strong base, it turns it into soap. And then what they'll do is they'll bleach the soap to get rid of any unpleasant animal or vegetable oil smells. They'll add some fragrance to it, and voila, you have soap. The next sort of key idea that we should look at is auto-ionization, because it forms the basis for what happens in acid-base reactions in water. Auto-ionization is something that happens to water molecules to a very small extent, but it's nevertheless important. That's one word, I don't know why I put that space there. At room temperature, which is 25 degrees Celsius, pure water contains 1.0 times 10 to the minus 7 molar of H plus concentration and OH minus concentration. So what's happening is that water molecules, two water molecules can collide, and on a rare occasion, one water molecule pulls a proton off the other molecule and you get a hydronium ion and a hydroxide ion. Obviously both of them are aqueous. And this occurs to the extent that they put a constant to it. So if you take the concentration of H3O plus and multiply it by the concentration of hydroxide at room temperature, it equals the number 10 to the negative 14 at 25 degrees Celsius. So this constant is an important aid to calculations involving acid-base theory. If the pH is 7, right, I'm just going to close the door. If pH is less than 7, then your H3O plus concentration is greater than 10 to the negative 7 molar. And if pH is greater than 7, then the OH minus concentration is greater than 10 to the negative 7. Obviously the H3O plus concentration is less than 10 to the negative 7. And if pH equals 7, then H3O concentration equals OH minus concentration, which equals 10 to the negative 7. Now they have a what's called a pH scale for discussing acidity, because pH varies over a huge range. It varies over a range of over 14 orders of magnitude. So they've developed a pH scale. pH scale says that pH, power of hydrogen is what it stands for, is equal to the negative log of the H plus or H3O plus, whatever you like, H plus concentration. Basically, H plus and H3O plus are interchangeable. Hydronium is just a hydrated proton. The idea of just one proton with no electrons floating around in the solution is kind of it's kind of stark. That doesn't really happen. But for mathematical purposes, it's fine. It doesn't create any errors in our calculations. At least not the ones we're doing. So look at the give it some thought on page 678. It says calculate the concentration of hydroxide in a solution in which H plus concentration is 2 times 10 to the minus 6. So, how do we do that? This is practice example on page 677 going to 78. First one, they say that the H plus concentration is equal to 2 times 10 to the negative 6 molar. Given that the H plus concentration times the OH minus concentration always has to equal 10 to the negative 14 in water, we can solve for OH concentration. So OH minus concentration is going to be equal to 10 to the negative 14 divided H plus concentration. So what you get is 10 to the negative 14 divided 2 times 10 to the negative 6, which gives you 5.0 times 10 to the negative 9 molar for the OH minus concentration. In part B, it asks calculate the concentration OH minus if H plus equals OH minus. Well, whenever H plus equals OH minus, in aqueous solution, it means you have a neutral solution, and it means that both of them are 10 to the negative 7. If H plus equals OH minus concentration, then it is a neutral solution. And in neutral solution, you have 1.0 times 10 to the minus 7 of both of these guys. So if you take the pH, you'll see pH of, which equals negative log of H plus concentration. If you take the log of 1.0 times 10 to the minus 7, that's how you get a pH of 7, which is considered neutral. Part C of the same question. I like this one, it's kind of cool. Part C of that question, it asks if the H plus concentration is 100 times the OH minus concentration. Well, the trick to doing this one is you say, okay, H plus concentration equals 100 times OH minus concentration. So let's let something be X. Let's learn how to spell too. Let X equal OH minus. Then X times 100X has to equal 10 to the negative 14, because one is representing the H plus concentration, the other one is representing the OH minus concentration. In aqueous solution, it always comes out to 10 to the negative 14. 3 viewers? That's scandalous. Where's the rest of the class? So then you multiply these two together, you get 100x squared equals 10 to the negative 14. And then you solve for x. Obviously x squared is equal to 10 to the negative 14 over 100, which gives you 10 to the negative 8. Oh, how did I get that? X squared is equal to 10 to the negative 16. So therefore x equals 10 to the negative 8. Right. And then therefore that's the OH minus concentration. So OH minus concentration equals 10 to the negative 8. So 100 times that gives you 10 to the negative 6. So that. Sorry, that's my uncle trying to call me. Let's hope he doesn't try again. I'll call him again in 10 minutes. So that concludes that calculation. You get 10 to the negative 8 and 10 to the negative 6. So, yeah, that was a cool question. The next give it some thought question says, what is the significance of pH? How does the pH change as OH minus concentration, as OH minus is added to the solution? pH, I'll answer that one orally. pH equals 7 signifies that the log of the H plus concentration equals negative 7. And therefore also the H plus concentration equals 10 to the negative 7, because the two have to multiply out to 10 to the negative 14. So it's a neutral solution. In part B, if OH minus, if hydroxide is added to a solution, that will raise the pH and make it basic. Small changes in pH can have a huge effect on the role of some reactions. So it takes very little acid or base to change the pH significantly when you have when you're close to neutral pH. Remember, 10 to the negative 7 is a very low concentration. So pH can vary pretty rapidly from around 9 to 5. From pH 5 to pH 9, it's pretty easy to make changes. our own blood is buffered at around 7.35 to 7.45. So our pH has to stay within that very narrow range, or else our enzymes start to malfunction. Our bodies only work at a very narrow range of pHs. We have special chemicals in our bodies called buffers that actually keep the pH in that range. And of course, as soon as our pH varies from there, we start to breathe faster to bring it back. So if our pH starts to fall below 7.35, we're going into what's called acidosis. We're actually getting too much acid in the body. So what we do is we start breathing faster to get rid of carbon dioxide, because by getting rid of carbon dioxide, we also get rid of carbonic acid. And carbonic acid helps. If you get rid of an acid, you bring the pH back up. If our body pH goes the other way, we go into what's called alkalosis. So if you get alkalosis, your body has other mechanisms to bring the pH back into alignment. But you can't have your pH change too far away from there, otherwise your enzymes start to malfunction, because your enzymes, being biological catalysts, are made of amino acids that are wrapped up into a three-dimensional shape. They're very sensitive to pH changes. They could change the shape of the enzymes, and when you change the shape of the enzymes, they don't work the same way. In fact, they might stop working completely. They can get what's called denatured. Well, maybe not denatured, but they can stop working optimally. There may be, it's probably a good reason why, if you get a virus, it's not a bad idea to let your fever go up, because it's your body's way of combating the infection. Not unless it happens to be a bird virus, in which case it's better to keep your fever low. So don't take medical advice from me. I'm just saying, this is things that can happen. Go to your doctor. Next thing we're going to look at is page 680. Yeah, page 680, practice example. It asks, in a sample of lemon juice, H plus concentration is 3.8 times 10 to the negative 4. What is the pH? All right, so I'll show you how to use that equation. So the H plus concentration is equal to 3.8 times 10 to the negative 4. And since pH is equal to the negative log of the H plus concentration, plug that in, you get pH equals the negative log of 3.8 times 10 to the negative 4. You enter that into your calculator, the answer you get is 3.42. Second question, they ask you what the pH is if your H plus concentration equals 5.3 times 10 to the negative 9. Again, you enter it into the pH equation. pH equals negative log of H plus concentration. Enter that in. You get negative log of 5.3 times 10 to the negative 9. The answer is 8.28. So that's a basic pH higher than 7. On page 681, they say if the pOH for a solution is 3, what is the pH of the solution? Now, pH and pOH are related by this equation. Very easy to remember. Number 14 always comes up. But read the book. pH plus pOH always equals 14. So if they give you the pH, they say the pH is 9.18, then the pOH I'm sorry, I'm looking at the wrong one. I jumped ahead. I'm actually doing the practice example at the top of page 681. There's another one that's called like, Give It Some Thought. It comes later on. But anyway, it's still relevant. We'll get to it in a minute. If the pH, it says, the solution is formed by dissolving an antacid tablet, has a pH of 9.18. Calculate the H plus concentration. So they say pH equals 9.18. And because pH is equal to negative log of H plus concentration, if you press the inverse log button on your calculator, what you're doing is you're taking 10 and you're putting whatever that number is to that, you're raising 10 to whatever power that number is. So in this case, what you would do is take 10 to the negative 9.18. Okay, that's the inverse log. That's what your calculator is doing when you press inverse log. So if they give you the pH and they ask you to find the H plus concentration, you got to use the log button backwards. If they give you the H plus concentration, they want to find the pH, you say log. You'll see it on your calculator. But when you look at that button closely, you'll see that it says on the log button as the second function, where is it? Yeah, as the second function to the log button, it'll say, I don't know if you can see that, 10 to the power of X. Come on, focus. My finger's in the way. Take my word for it. So what you get is that your H plus concentration equals 6.61 times 10 to the negative 10 molar for that one. Then for the next question, for the give it some thought, it says, if the pOH for a solution is 3, what is the pH of the solution? Okay, well, I just gave you the solution. The answer for that is pH plus pOH always equals 14. So they tell you that pOH is 3. So 14 minus 3 gives you the pH. pH is 11 in this case. And if the pH is greater than 7, it means that the solution is basic. pH greater than 7, it's a basic solution. There's a few ways of measuring pH. You can do it with a pH meter, which is basically a voltmeter. It's calibrated to detect the presence of H plus ions. Another way of measuring pH is to use litmus paper. Litmus paper turns red when the pH is below 7, around pH 5, and it turns blue when the pH is around 8. So litmus paper, but that's kind of a qualitative test. And then you can also use indicators. There are indicators that change pH, change color at different pHs. So according to where your titration pH is supposed to be, you can pick an indicator that will turn color at the appropriate time. On page 682, it asks, if phenolphthalein turns pink, you know that phenolphthalein is an acid-based indicator, but it used to be used as a laxative. Interesting, isn't it? If phenolphthalein turns pink when added to a solution, what can we conclude about the pH of the solution? Well, it means that the solution has a pH greater than 7. So that's a qualitative assessment. You're not getting an accurate number, but in some cases, that's all you really need. You know, if you're a lifeguard, one of the jobs they give you as a lifeguard is to check the pH of the pool water. pH of the pool water can't get too acidic or basic, because then, you know, the swimmers' eyes will burn. You'll bleach their clothes and do all sorts of stuff to them that aren't necessarily good. But you also have to make sure that it's not toxic to your skin. I think what they normally do is when there's no people in the pool, they'll add a bunch of bleach-like chemical to kill all the bacteria in the pool, and then after that pool has been treated, obviously they're continuously filtering it, then they readjust the pH back to closer to a physiological pH, so it doesn't burn your eyes as much. But there's still stuff in the pool that will that oxidizes and bleaches, just to keep all the infectious organisms from your body from infecting somebody else's body. The strong acids and strong bases, you already know them by heart, and you know the mnemonic: NACRB, Casterba for the bases, no-so, clock-lock-will-breed for the acids. But just for fun, let's put them up. You know them all. If you don't know them, then I don't know what you've been doing in my class. Those strong acids is no, so, col-breed. Write an H in front of everything. Hydrogen gets 2, sulfuric acid gets 2, and it goes 3, 4, 3, 4. Nitric acid, sulfuric acid, chloric acid, perchloric acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid. Those are all the strong acids. If it's not a strong acid, it's a weak acid. Okay? Then the bases, strong bases, I gotta make room. Strong bases go Nakerb, Kasserbach. Put an OH. These are 3 from group 1 metals, these are 3 from group 2 metals. So these ones have a +1 charge, these ones have a +2 charge, so they get 2 hydroxides. Okay, so sodium hydroxide, potassium hydroxide, rubidium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. I'm not going to write all of them. Okay, when a strong acid or base is dissolved in water, H plus, oh my gosh, already 31 minutes. H plus or OH minus respectively will equal the concentration of the acid or base that was dissolved in the solution. So if you have 1 molar potassium hydroxide, you're going to also have 1 molar hydroxide because it dissociates completely. I'll give you some homework right away. Try practice example page 683 and 684, and tomorrow I will answer. So for homework, practice example page 683, 684. And then we can move together through this chapter. Also, I strongly recommend you copy the notes from the upload I did for chapter 4. I'm also going to create a playlist so you can find all the chapters there. I haven't finished chapter 16. I've only done the notes, but I'm going to start doing the problems as well. Because like I said, I left my binder in Toronto. I'll see you tomorrow, guys.